All right. Today we're going to prove this majority of Stablest theorem that was mentioned back in lecture 10. So one motivation for it is from all the stuff we were doing on constraint satisfaction problems and hardness for them. In particular, it's motivated by what is, in some sense, like the world's simplest constraint satisfaction problem, namely max cut. I think we mentioned it when we talked about CSPs, but I'll just remind you, it's the CSP where the domain for the variables is just of size 2, which is kind of the least you could imagine, minus 1 and 1, say, and there's only one predicate, and it's like the not equals predicate, which is also kind of the simplest one you could imagine being a binary predicate. So in particular, it's a CSP where all of the constraints look like this. V1 does not equal V5. V3 does not equal V4, V2 does not equal Vn, and so forth. So that's the input, and you try to assign plus or minus 1s to the variables to satisfy as many of the inequalities as possible. And of course, you can think of the variables as vertices of a graph, and the assignment as a partition of the graph into two parts, and you're trying to maximize, and each constraint is like an edge. You're trying to maximize the number of cut edges. Okay, so it's almost as simple as you can get for a CSP. Nevertheless, the best algorithm, approximation algorithm known for it is somewhat complex. So you may have heard of it. This is an algorithm due to Gomans and Williamson from '95. And it achieves the following guarantee. For all, and this is a little bit weird, it's parameterized by, the statement is parameterized by a value of rho that's negative. It's between minus 1 and some rho star, which is about minus 0.69, you can approximate max cut like this. So you can 1 minus arc cos negative rho over pi out of a half minus a half rho approximate max cut in polynomial time. So I'll remind you what this means. Well, it means that given an instance where it's the best partition or the best solution satisfies this fraction of constraints, the algorithm is guaranteed to find you a solution that satisfies at least this fraction of constraints. It still looks quite opaque, I imagine, so let me draw a picture. Okay, so let me make this the rho axis, and we're actually interested in it going from minus 1 to some minus 0.7, but I'll draw all the values between minus 1 and 1. So half minus a half rho is like a linear function that looks like this. Okay, you can hear my voice.
Yeah.
Okay, no problem.
Sorry.
No problem. Okay, so try to be extra careful about what I say. So this is the plot of half minus a half rho. This goes up to 1. This is 0. Okay, and let me draw a picture of this plot for you. It looks kind of like this. It's like a cosine curve turned on its side because of the inverse, so it looks like. Okay, and this funny number, minus 0.69 whatever, happens to be the point where if you drew a line from here, it would be like tangent to here. That's like the definition. Okay, so this is rho star, which is whatever, minus 0.69. Okay, so just, squinting at the picture, if the maximum fraction that's satisfiable in the instance is here, the algorithm gets at least this red curve. Okay, so it's some kind of guarantee. And in particular, the ratio between this number and this number, which is the ratio of those two things, is this number that's like 0.8786 or so. Okay, so it has the property of this algorithm that whatever the optimum is beta, it's guaranteed to get at least a 0.8786 times beta fraction of the constraints. Okay, so these are some peculiar numbers, and indeed it's kind of a sophisticated geometric algorithm. In particular, let me also just highlight one number that I like. If you apply this theorem with rho equals, okay, you need a number that's like a little bit less than negative 0.69. So one nice such number is negative 1 over root 2. Okay, and so this leads to Somebody know arc cos of 1 over root 2? It's like an isosceles right-angled triangle. OK, well, it's pi over 4. So this becomes 3/4. And this becomes half plus a half over root 2. So in particular, if this is like 0.85 or something, if 85% of the constraints are satisfiable, this algorithm gets 75% of the constraints. OK. So the theorem that we'll sort of ultimately prove today is that there's a matching unique games hardness result for this algorithm. OK, that is to say, for all rho actually in this range, well, let me just say between -1 and rho star, although it also holds for between -1 and 0. And for all epsilon greater than 0, doing any better than this, 1 minus cos inverse minus rho over pi plus epsilon out of half minus half rho minus epsilon is, at least as hard as the unique games problem. OK, so in particular, if you believe the unique games conjecture, that this is equivalent to NP hardness, it kind of gives like an awesome-looking statement. This is the simplest CSP in the world in some sense. Yet, the true behavior of like how well you can approximate it in polynomial time is given by all these like weird arc cos numbers and so forth. OK, any questions about that? OK, so as you remember from our discussions of unique games hardness, in order to prove such a result, such a hardness theorem, it suffices to construct these dictator tests that are appropriate. OK, so I'll remind you about that as well. But basically, to do this, it suffices to construct an appropriate we call them dictator versus no notables test. OK, and so what is this? It's a test for an unknown Boolean function. It's in the function testing regime. And in order to get a max cut hardness result, this is our predicate. So the test has to make two queries on some strings x and y. And it has to accept if and only if f of x does not equal f of y. OK, so we want our test to be two queries like that. And we need the following properties. That the probability the test accepts f is at least this larger number, half minus a half rho, if f is a dictator. And we need that the probability that it accepts f is at most this smaller number, 1 minus whatever, plus some error term, lambda of epsilon, which goes to 0 as epsilon goes to 0. When f has no epsilon notable coordinates. OK, so this is going to be our test. We're going to check this in 1 second. It's very easy. And then the whole main part of the work will be going in to show this. OK, that if you're somehow far from being a dictator, then this is somehow measuring your noise sensitivity or stability, then this probability of acceptance will be a lot lower. OK, so given f, the probability that this test accepts f, well, it's very easy to see. Rho correlated. We'll just make a number which is 1 or 0, depending on whether or not f of x equals f of y. So that's half minus half times f of x, f of y. It's 1 if they're unequal and 0 if they're equal. So it's a half minus a half, the expectation of f of x f of y. And this is when x and y are row correlated. So this is a half minus a half the noise stability at row of f. OK, so of course we know that if f is a dictator, then this noise stability row of f is just rho. So the probability of acceptance is in fact equal to half minus a half rho. And it's also clear combinatorially from the definition. That's sort of how we set up the test. OK, so this part is OK. OK, and so for this part, you see we just need to like lower bound the noise stability. Because of this minus sign, I say lower bound of functions that sort of have all their coordinates not influential. OK, so more precisely, to prove this theorem, which I'm erasing, get the hardness result for max cut, which matches the Goens-Williamson algorithm, via proving this result about a dictator test. What remains is to show if f has no epsilon epsilon notable coordinates, or to say it according to the definition, if the influence 1 minus epsilon stable influence of each coordinate is at most epsilon, then we want this acceptance probability, half minus a half times the stability at row of f, to be at most this second number, 1 minus cos inverse minus rho over pi, plus some term that goes to 0 as epsilon goes to 0. OK, it looks like a lot of symbols, but I'll get rid of some of them shortly. OK, any question about that? Hopefully it'll become a little clearer as I do a few more manipulations. OK, so actually, let me just rearrange this a little bit. It's I find it very annoying to have think about noise stability with a negative value of the parameter. That's kind of stressful, so I'm going to get rid of that in a second. OK, so let me just rearrange this a little bit first. That's the same as saying negative the stability of row of f is at most 1 minus 2 over pi cos inverse minus rho. It's just arithmetic. OK, and this thing, negative the stability of rho at f. So it's negative the weight at level 0 minus rho times the weight at level 1 minus rho squared times the weight at level 2 minus rho cubed times the weight at level 3, et cetera. OK, and remember that rho is negative. OK, these weights are non-negative. So this term is negative. This term is positive. This term is negative. This term is positive, and so forth, because rho is negative. So I'm just going to drop all the negative terms. OK, and say that this quantity is at most what I get if I dropped all the negative terms. So this is like negative rho times, maybe I'll write it like this, negative rho times the weight at level 1 minus rho cubed times the weight at level 3. OK. And so this I claim is actually the noise stability at negative rho of, well, let me just write it, the odd part of f. Okay, you'll have to remember all your formulas from homework 1 for this. I'm just doing some annoying manipulations here. But remember, if you have a function f, you can take its odd part, which is really defined by f of x minus f of minus x over 2. But you can also obtain it just by dropping all of the even parts of the Fourier expansion. And then you see this would give you the noise stability at negative rho of that function. OK, and this I like better because now, since rho is negative, negative rho is positive. So I feel like it's a more natural thing to look at. OK, so given that, I'm going to prove a slightly stronger result that will imply this thing. So what I want to say is, therefore, we'd be done if we can show that for all odd f, if you have a function f whose range is plus or minus 1, and you take its odd part, remember it's defined by like f of x minus f of minus x over 2, its new range will actually be minus 1, 0, or 1. So in fact, I'll just prove something for functions whose range is the interval minus 1, 1. Such that we have this condition on their influences. For all rho, let me say it like this. Actually, sorry. Let me switch to positive rho now. The noise stability at the positive value is at most this thing, 1 minus 2 over pi cos inverse rho. Okay, what I'm saying, this is what I would like to prove, and I feel happier about it because it has a positive value of rho for the parameter. I'm going to prove this, and having done that, it'll give me this by applying this theorem to the odd part of f. Okay, you actually also have to check that if you have a function, all of whose stable influences are small, and you take the odd part, the stable influences remain small. But actually, that's clear because you get the odd part of f just by dropping parts of the Fourier coefficients, the Fourier expansion. So that can actually only make the influences, which are like sums of squares of Fourier coefficients, go down. Okay, this is a somewhat boring manipulation. If you didn't quite follow it, it's not super important. This is what we're going to show. And it implies the analysis of the dictatorship test and therefore the UG hardness result. Any questions? No? It's all great. Okay, great. Okay, actually, we don't even need f to be odd. The only thing we're going to use about it is that it has mean 0. Okay, so let's just stare at this again to look at what we now want to prove. You're looking at Boolean functions. You can forget about the fact, if you want, that its range is this interval and just think of it as being a Boolean valued function. Okay, so imagine you have such a function, and it's mean 0, so it's true on half the cube and false on half the cube. And all of its influences are small. Rho is some medium number. You can think of my favorite number, 1 over root 2. Okay, then you're trying to show that its noise stability, which, if it were a dictator, could be as large as rho, or 1 over root 2 in this example case, is in fact bounded by this smaller number if it's far from being a dictator, which is like half in this case of this rho. Okay, and this is, you may also remember, this quantity we proved way back in lecture, I think, 10. This is the limiting value of the noise stability at rho of majority on n coordinates. Okay, so this theorem, this majority is Stablest Theorem. Okay, and its name is because, it sort of says if you're a function with all your influences small and, let's say, mean 0, your noise stability is essentially not much more than the noise stability of majority. So essentially, majority is like the most noise stable, non-dictatorial function. Maybe that's also a good justification for using majority in actual social choice election schemes as well. Okay, all right. So there's no questions about that, then we'll spend the rest of the class proving this.
So if you look at functions with standard influences smaller than epsilon, is this
No. Actually, this is still true if you put this in here. Well, this is a... Yeah, you're saying if you take this out, then you're either allowing more functions or allowing less functions. One of the two. But it doesn't matter. The theorem is the same, actually, if you put this in or not. Yeah, I guess it would be stronger. The theorem would be stronger if you didn't have this. So it's also true in that case, too. I just put this, well, I just had this in here mainly because of the application to the dictatorship test. Yeah, we'll see this idea, in fact, when we go through the proof. What's the difference between the influences and these like stable influences? It only makes like a big difference if the function has like a lot of Fourier weight on really high degrees, right? You know, that's the case in which this attenuating factor makes a difference. But if you have a lot of weight on really high degrees, then your noise stability is going to be small anyway. I mean, at a high level, it's going to be small anyway. Like if it's parity or something, all the Fourier weight at up high, its noise stability will be small anyway. We'll kind of actually use that idea in the proof. OK, great. So how are we going to prove this? All right, well, you may not be surprised in light of what last lecture was about, this invariance theorem. We're going to prove it using this invariance principle from last time. So this invariance principle we saw last time at a very high level, I mean, it sort of told you that if you had a function, f, which you can think of maybe as a multilinear polynomial, and all of its influences are small, then the distribution on what you get if you like plug bits, random bits into it, into the n coordinates, and the distribution that you get if you plug like independent Gaussians into it is somehow not too different. And so we're going to use that fact to convert to this problem about functions on bits to a problem about functions in Gaussian space. Okay, in Gaussian space, you'll be able to use some geometry to help solve this problem. Okay, so let me tell you what this sort of Gaussian analog of the majority of Stablest theorem is, which we're going to use to prove our result. It's a theorem that, in a special case, was on one of your homeworks, homework 5, number 6, if you remember that. So hopefully this will look slightly familiar. We're going to use a theorem due to Borel, Christopher Borel, from 1985. It's a kind of isoparametric inequality for Gaussian space. And a special case of his theorem says this. Let f be a function from Rn into -1, 1. And again, you should probably just think about the case where f's range is plus or minus 1, the set. So f is like the indicator of some subset of space. And let's assume that it has sort of mean 0 on Gaussian inputs. Okay, well, okay, where this z vector is n-dimensional Gaussian. Okay, so think of it as an indicator of a subset of space, and this says that it's sort of has Gaussian volume 1/2. If you pick a random n-dimensional Gaussian, each coordinate is Gaussian. 50% of the time it'll land in the +1 side, and 50% of the time it'll land on the -1 side. Okay. And the theorem is that what you might call the, well, actually for all positive rho, something that you might call the Gaussian noise stability of this f at rho, which looks like noise stability only with Gaussians. Well, let me finish writing it over here. Is at most this magic number, 1 minus 2 over pi arc cos rho. And here, z and z prime are rho correlated Gaussians. Okay, so I hope you at least vaguely remember this concept of correlated Gaussians. This means that z and z prime are both n-dimensional vectors in Rn. They're random vectors. And on each coordinate, zi and zi prime, both of these guys have the Gaussian distribution, n0, 1, but they're not independent. They're correlated such that the expected value of zi prime is rho. Okay, and it's like this on all n coordinates independently. So basically, z and z prime are both random Gaussians, but they're correlated, so they sort of point, since rho is positive, they point sort of vaguely in the same direction. In particular, if rho is really close to 1, they're like almost the same vector. And as rho goes towards 0, they become like independent vectors. Okay, and this is, as I said, sort of an isoparametric statement. Again, if you think of f as being the indicator of a set, this is like the probability that z and z prime are either both in or both out. So sort of like they fall into the same side of the sets. Okay, and if you think of rho as like some medium number, it's like you pick two correlated Gaussians and ask what's the probability that they're both in or both out of the set that f is indicating. Okay, and it gives this upper bound. And the thing on the right side, this is a sharp upper bound in the sense that there's some function f which achieves this. And the thing on the right side, this is exactly, it's not a good marker. This is exactly the sort of Gaussian noise stability at rho of a half space. Okay, since Gaussians are rotationally symmetric, it doesn't matter which half space you mean. So take any hyperplane through the origin and let f be the plus or minus 1 indicator of that half space. And that's the function which maximizes this probability that two correlated Gaussians will either both be inside or both be outside. Okay, and the fact that it achieves this value is exactly this Shepard's theorem that we also proved way back in lecture 10. In fact, this is how we deduce the fact that the limiting noise stability of majority is this number. We use the central limit theorem to like reduce this to the problem of calculating the Gaussian noise stability of a half space. Okay? Because remember, majority is really like a half space. It's the sign of a linear form. Okay, so if you don't remember this stuff, you can go watch the lecture 10 video again. Okay, so this is a fact about Gaussian space, that sort of half spaces are the best sets for this kind of isoperimetry. And I'll remind you that you actually proved this theorem, this very theorem, for certain values of rho. So you proved this for rho such that cos inverse rho is of the form pi over 2 times an integer. Okay, this is on homework 5. Okay, so one example of 2 times an integer is 4. Cos inverse of pi, cos of pi over 4 is 1 over root 2. So in particular, this proves that for rho equals my favorite 1 over root 2. Okay, so in fact, you can push this all the way through and get like the hardness result for max cut. That's this 3/4 versus half plus 1 over 2 root 2. Oops. The ratio of which is 0.8786, no, 7. So it's essentially the optimal unique games hardness result. Okay, and this proof from the homework is a very simple like triangle inequality argument. I don't know if you remembered it, but it's quite easy. To prove it for all rho, not just ones that are of this special form, Borel and also Beckner later proved it by symmetrization arguments. And there's another argument using Boolean functions and induction that came out on arXiv like a couple weeks ago due to Day, Mossel, and Niemann. So that's a nice paper you can take a look at. But we're just going to take this as a given since, we've proved some interesting cases of it already. OK. Any questions about the statement of this geometric theorem? What we're going to do for the rest of the class to try to prove this theorem about Boolean functions is use invariance to sort of convert this question to a problem about Gaussian space and then apply this theorem. All right. OK. So let's go into the details a little bit more carefully than just the one-line summary that says use invariance.
Hey, Ryan.
Yeah.
So, mean of dictator is also 0 or not?
Yes.
Okay, so a little confused.
So in Gaussian space, there's no such thing as a dictator. Like if you just output, that's a good point, excellent point of fact. If f just is like the function f of x equals x1, then that function is not bounded in -1, 1. Okay, so this is really, it should map every point to between -1 and 1. So when the domain of the function is Rn, this function, which I guess you could call a dictator, is not bounded. So you cannot you're not allowed to choose that function.
No, but what if xi is positive, then it's +1?
Right, so you're saying, OK, what about instead f of x equals sine of x1? That's valid. And that's this function. That's a half space. It's the half space which is, perpendicular to the first direction. And if you do the calculation, you'll see that its noise stability is exactly this number.
Because it looks like a dictator to me, but it's not dictator.
Yes, it's not. Because x1 is Gaussianly distributed. So this is somehow more analogous to the function which is sine of x1 plus dot 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 plus xn over root n. If these are, maybe I should write z1 here. If these are bits, then this thing is kind of distributed like a Gaussian. So sine of one Gaussian is kind of similar to sine of x1 plus dot 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 plus xn, which in turn is like the majority function. Not exactly sure if that clears it up, but somehow it's there is no dictator in Gaussian space. There's just half spaces. OK. All right, so let's do more proof ideas. OK, so this is the theorem we're trying to prove. So let's say we're given f. OK, think of it as a multilinear polynomial. By which I guess I just mean think of its Fourier expansion. But that's a multilinear polynomial. And you can interpret that as a function on Rn. Okay. Now, when you interpret it as a function on Rn, it'll probably no longer be bounded by -1, 1 everywhere. But we'll come back to that. So still, invariance, the idea of invariance is you're going to take this multilinear polynomial and actually look at f of what you get when you plug in Gaussians for it. So one thing we can ask ourselves is, this Gaussian noise stability of f, the expected value of f of z prime, where z and z prime are row correlated Gaussian vectors. You might ask, I wonder if this is maybe equal to or related to the stability of the noise stability of f as a Boolean function. What you get if you plug in, well, if you do the same experiment but with correlated bits rather than correlated Gaussians. In fact, what I would like to tell you is that it's not just approximately true. I mean, this is actually equal. Okay, so for multilinear functions, these two quantities are exactly equal. And the reason is both of them are equal to this formula, this Fourier formula, sum over S rho to cardinality of S f hat S squared. Well, this is the Fourier formula for the noise stability of f when you think of it as a function on bits. But if you remember how we proved that formula, it was really some just like Parseval type thing, right? Where you looked at expected value of f of x and f of y, where x and y are rho correlated. You took the multilinear expansion, you expanded it all out, and it really just relied on the fact that you had, expected value of xi, yi equals rho, and expected value of xi squared equals 1. And this is still true if you use Gaussians instead of bits. Okay, so again, if f is a multilinear polynomial, then the Gaussian noise stability of it is actually the same as the Boolean noise stability. So then that kind of looks good. It almost seems like we're done, right? We have this function f. It's a Boolean function. We sort of think of it as a multilinear polynomial and expand it to a function on all of Rn. And then we know that sort of the Gaussian noise stability of that thing is the same as the Boolean noise stability, which is what we're trying to bound. So why don't we just use this theorem and we're done? Right, that's the problem. So the point is, yes, this Boolean function you start out with, it's bounded between -1 and 1, like on these 2 to the n points in Rn, like these corners of the cube. But then if you extend it, I mean, if you just now think of it as a multilinear polynomial and interpret its domain as Rn, like it's not going to be bounded between -1 and 1 everywhere. Like the function could just be like f of x equals x1. And then as we saw, if you plug in a Gaussians, or if you plug in like you could plug in like x with like 3.6 as its first coordinate or something. So you cannot apply Borel's theorem to this thing. OK, well, I mean, I guess it's kind of clear we couldn't have been done. We didn't use invariance anywhere. So the actual idea is the following. We know that with this f, thinking of it as a multilinear polynomial, if you plug in random plus or minus 1 bits, this is always between -1 and 1. Think of this as a random variable. It's always between -1 and 1. And what does invariance say at a high level? If the function has like low influences, the distribution you get when you plug in Gaussian should be like similar. So you may hope that invariance implies that f, when you plug in, Gaussian, z1 through zn, sort of, this thing is between -1 and 1, let's say almost always. It may be true that on all of Rn, like this function f is not bounded, but maybe if you plug in like Gaussians, maybe it'll sort of usually be bounded. So that wouldn't be the case if f of x were like f of x equals x1. I mean, there's a good chance if you plug in Gaussians here, that the first coordinate will not be between -1 and 1. But that's OK, because this guy does not have low influences. We didn't expect that to happen. But this is what we sort of hope will happen. And in that case, I mean, suppose this is like the main work. Suppose that happens. Here's going to be the idea. We're going to define a function, let me call it f bar from Rn into -1, 1, which is just f bar at an input z. I was just in Canada this weekend, so I'm slipping. Will be the truncation to -1, 1 of f of z. Okay, this thing. Okay, this is a little function I invented. Hopefully, you'll know what it means by the name. It's the function that looks like this. Okay, that's 1, minus 1, 1, minus 1. So it's the function that you give it an input. If it's between minus 1 and 1, it just gives that input back. Otherwise, if it's bigger than 1, it truncates it down to 1. If the input is smaller than minus 1, it truncates it up to minus 1. OK, so you kind of hope if z is a random Gaussian that this random variable f of z is almost always between minus 1 and 1. So therefore, you hope that this f bar, this modification, which like truncates the range to always be between minus 1 and 1, somehow this random variable f bar of Gaussians is like close to f of Gaussians. Sort of going backwards on the boards here, but. OK, so what we would hope to show is that, indeed, we hope, because of invariance, that this is true. And therefore, this function defined by truncating f of z to be between minus 1 and 1 is close to f of z. So hope that the following holds. More precisely, by this I mean the expected value, let's say close in L2 squared distance. OK, so close in the sense that if you pick a random Gaussian z and you look at f of z and f bar of z, maybe you square the difference, in expectation that's very small. OK, so that this, sort of somehow for most z, this truncation doesn't really do anything. And I'm going to put a little star around this thing because it's sort of the linchpin of what the argument's going to be. We're really going to hope to use invariance to establish this fact. Does that make sense? And why does that make us happy? Suppose we manage to show that if you take this low-influence Boolean function, you extend it multilinearly to all of R of n, and then you just make f bar, which truncates it to minus 1, 1. That's close under Gaussian to the original f. Then this Borel theorem, we can apply it to f bar. So it implies that the Gaussian stability at rho of f bar is at most this magic number, 1 minus 2 over pi cos inverse rho. OK, that's actually, well, that's assuming that expected value of f bar is 0. Right? Borel's theorem says this is true if the mean of f bar is 0. Let me come back to that. It's a very minor point in it. Let's assume that for now. And then we might hope that, therefore, by star, I'll fill in these details in a second, but we feel that f bar is very close or similar to f. We might hope that that means that the noise stability of f is also bounded by this, maybe up to this error term, little o of 1 with respect to epsilon. And then as we saw, this is actually identical. It's equal to the rho noise stability of the f as a Boolean function. Okay, and that would be the desired result. This is sort of the overall plan for the proof. Does it make sense? Where? Second time you wrote 2 over pi. Yeah, thanks. Oh, and on this minor point, well, let's think about it for a second. Another thing that I claim that's very similar to this, only easier, is that the expected value over bits of f of x is the same as the expected value over Gaussians of f of z when, again, you identify f with its multilinear expansion. Can somebody tell me why that's true? Yeah, it's just the constant term. I mean, if you have, if f is something like f of x is, I don't know, 3 plus x1, x2 minus 5, x1, x3, x9. Okay, we know when you substitute in random bits for x in expectation, all these things become 0, and you just get the constant term. It's because the bits are independent and have mean 0. But this is also true of Gaussians. If you substitute in independent Gaussians, they're independent, and they also have mean 0. So everything other than the constant term goes away. So in particular, we certainly know that the expected value of f of x, which by hypothesis is 0, is the same as the expected value over Gaussians of f of z. Okay, and so again, we may hope that if f and f bar are somehow very close, if f's mean under Gaussians is 0, then f bar's mean under Gaussians should be close to 0 at least. Okay. Well, that's the plan. And now I'm just going to use the rest of the class to fill in as many details as I can. I don't know if we'll get through all of it, but I'll just say, actually, there's some people in math that like algebra, and some people that like analysis. And they're kind of different. And I like analysis because I feel like you can always try. If you're trying to prove some theorem, you can mess around, make this approximation, make that approach. You can attempt to prove your theorem by hard work. Whereas in algebra, I feel like you either get the exact theorem proof like that, or it doesn't work. Somehow you don't prove the C law of theorems by just messing around. Yeah, but in analysis, you get to just work hard and mess around until you get what you want, and that's sort of what the rest of this proof is like. So, that's what we'll do.
By the way, are you going to come back to this point of being, if it's approximately 0, that's also okay?
Yeah, I will. Yeah. Well, I'm going to try. Yeah. This is, okay, first I gave the one-sentence plan, and then this is sort of the two-board explanation of the plan, and now I'm going to try and actually fill in the details. Maybe it would have been better if I had been majority of Stablest, proof. Let this be this, and let this be this, and go forward. Actually, I'm going to do it in perhaps a pedagogically horrifying style of just making more and more observations until hopefully you agree that the theorem has been proved. But I don't know. I feel it's better this way to sort of see the idea of the proof come out as organically rather than the top down. So yeah, I'm going to try and actually do the proof. Okay, so now let's do maybe all of the details. Okay, this is our hypothesis. We have some mean 0 function f whose range is -1, 1. These attenuated influences are all smaller than epsilon. Rho is some fixed number between 0 and 1, an absolute constant. We're trying to bound the stability at rho of f by this funny number plus some term that goes to 0 with epsilon. Okay. Yeah, so actually let me get to the thing that Anke was asking about. Let's actually imagine we get to this point. Okay? That's actually most of the hard work, to use invariance to get to this point, but now let's finish the rest of it more properly. Okay, so this part is a little bit fishy, and this part is also a little bit fishy, so let me clear that up. Okay, so one thing that is true is that the expectation of f under Gaussians is 0. That's that argument we made over there. And we're hoping that the star at least implies that the expectation of f bar is close to 0. And indeed, that's true. Okay, so it need not actually be exactly 0 if you truncate f. But let's just see that the expectation of f, everywhere I write expectation here, it's with respect to Gaussians. Let's look at how much it can differ from the expectation of f bar and f. Well, this is just 0. Okay, well, this is at most certainly the expected value of f minus f bar in absolute value. These are really of z. That's the triangle inequality. And now I can use Cauchy-Schwarz. So that's at most expected value again over z of f of z minus f bar of z squared. Okay, and that, assuming we get to star, is indeed like some little o of 1 quantity, little o with respect to epsilon. Okay, so this is at most square root of little o of 1, which is also little o of 1. Okay, so this little observation shows that indeed f bar's mean will be almost 0. And how do I want to conclude? I want to claim, maybe this is very slightly sketchy, but I think you'll believe it. I claim that you can just adjust f bar so that its Gaussian expectation is exactly 0 while preserving star. Okay, so we know its mean is almost 0. Like imagine it's 0.00001, so it's like slightly above 0. So now like take some places where f bar was positive and just make them like, I don't know, -1 there. So change it on like a little tiny fraction of the input space so that its new mean is exactly 0. Okay, and you've changed it on only a little o of 1 fraction of space. So this is maybe, I don't know, go up by a factor of 2 or something, but it won't change much. So what I want to claim is you can now adjust f bar so its mean is exactly 0, and you'll still have star up to maybe some slightly different little o of 1. Okay, so then if you have that, then this part is OK. I mean, that part is truthful. Okay, so it remains to check this part. And this will in fact also follow from star. Okay, so I want to just show that if f and f bar are close in L2 squared, then their noise stabilities are also close. And to show that, well, the difference between the two noise stabilities well, it's the expected value of f bar z prime, where z and z prime are row correlated, minus the same thing for f's. Okay, and one thing that you can do if you see something like this, where like two things are a little bit different, you just like insert a term in the middle that like helps you step from here to here. Okay, so I'm going to subtract the expected value of f of z, f bar of z prime, and I'll add it back in again. Oops. Yeah. Okay, so now let me just let me call this difference 1 and 2, and I'll show that both 1 and 2 are small using star. Okay, so 1 is the expected value of f bar of z minus f of z times f bar of z prime. Okay, linearity of expectation. And since I feel that this is small on average, I should do Cauchy-Schwarz. So by Cauchy-Schwarz, this is at most the square root of the expectation of f bar of z minus f of z squared times the square root of the expectation of f bar of z prime squared. Now, f bar is this function that's truncated to be between -1 and 1. So this quantity is always at most 1. So this whole expectation is at most 1. And by star, the assumption, this thing is smaller than little o of 1. Okay, so this whole thing is less than the square root of little o of 1. So it's little o of 1. Okay, so for this first difference, it's small. And the second difference is kind of the same. You'll just have, this will be like f of z. And here you'll have this with z primes. So you can do Cauchy-Schwarz again. Remember, z and z prime are both distributed as Gaussians. So it'll be the similar thing, except that you'll have expected value of f of z squared here, rather than f bar of z. So now we can actually say that f bar was bounded between -1 and 1. F is not bounded between -1 and 1. So it looks potentially a little bit harder. This could be bigger, but it's still OK. Can somebody tell me why? I claim that this term is still at most 1. Well, the reason is a little bit like these things on the board. You see, f is a multilinear polynomial. You're looking at the expected value of f on some random variables, independent random variables squared. I claim that this is still equal to sum of f hat s squared, as if it were Boolean inputs. Just because, if f is a multilinear polynomial, if you expand everything out using the fact that zi's are independent and have mean 0 and variance 1, you again get this sum of squares of coefficients formula. And this thing is at most 1 because it's actually equal to the expected value of f of random bits squared. And f on random bits squared is between -1 and 1. OK, so both of these terms are small, so that really justifies this. So we're done if we can show this fact by invariance. Any questions about that? I have a feeling I won't quite finish, but well, you'll get enough of the gist of it. So let's talk about invariance, since that's the main piece that we need. OK, so I'm hoping to use invariance and the assumption that f has low influences to show this, that f is close to, in Gaussian space, close to its truncation to -1, 1. First thing I want to say is that this condition star that I'm shooting for is equivalent to saying that the expectation under Gaussian z of psi of f of z is small, where psi is a special functional I'm trying to set it up so it looks like invariance. It's the functional that looks like this. It's 0 between -1 and 1. And then it looks like a parabola out here. Okay, this is a plot of the graph of some function I just made up, psi of t. And I claim that really star is identical to this statement. Okay, because what's happening here, if you take this f of z and plug it into psi, it's like if f of z is between -1 and 1, you pay 0. Okay, and f of z is, let's say, bigger than 1, you pay sort of the square of the distance from 1. Okay, and if f of z is smaller than -1, you pay under this functional the square of your distance to -1. And that's exactly what's going on here, right? Because f of bar of z does nothing if f of z is between -1 and 1, and otherwise it truncates it to the appropriate value of 1 or -1. Okay, so star is literally saying this. Okay. So that's good, because if you remember the invariance stuff, this is kind of familiar looking. So hopefully invariance will show, well, this is not quite right, but that the expected value of, under bits, of psi of f of x is somehow close to the expected value under Gaussian of psi of f of z. And that would be great, because what is this left-hand side? 0. That's right. It's 0, because our assumption is that f, when you evaluate it on bits, is always between -1 and 1. So This will always be between -1 and 1, and so this quantity will always be 0. Okay, so invariance would indeed, if we could get it to work, show this is close to 0, which is what we're shooting for. Okay, there's one small problem and one large problem with this plan. The small problem is that, remember when you're doing invariance, like you needed to use a functional psi, which was like C4 and had like its fourth derivatives bounded by some constant. Well, this function is not quite C4. It's continuous, which is a plus, but it's not really differentiable here and here. So it has like a little problem. Yeah, maybe it's C2. Okay, so this is a small problem. If there were more time, I would fix it, but you get around it by a similar hack as what we did before. It's actually an easier hack because it's continuous. You replace it by some other function, which is C4, and you smooth it out a little bit here. So, there exists actually some psi twiddle such that it's really close to psi, and its derivatives are bounded by something that's not too big. 1 over delta for any choice of delta. Okay, and you apply invariance with this functional instead of psi, and you incur a little bit more error. That's not really a problem. Okay, the bigger problem is that probably like the number one hypothesis of this invariance theorem is not satisfied. The number one hypothesis of the invariance theorem is that f is a polynomial of low degree. Right? Well, at least the error on the right-hand side was like 9 to the degree. And f does not have low degree a priori. It could have any degree. Like, I guess it has degree maybe n at most, but you do not want to pay a factor that's like 9 to the n. So that's a shame. Okay, so that's the main annoying technical task, is to fix that. But this gets back to somebody's point, Mahdi's point from the beginning of class, which is that you feel that somehow if f had not just had high degree, but sort of genuinely had high degree, had a lot of Fourier mass and high degrees, then it would have small noise stability anyway, so we somehow wouldn't have to really worry about it. We feel that if it's going to have a chance to have high noise stability, it should have almost all of its Fourier mass down low. And so that, let's say, if we just truncate away the high degree part, it shouldn't change f much. So that's the idea of this part of the strategy. Let me remind you the invariance principle that we're trying to use. This is from last time. It says that, let me write, if h is a multilinear polynomial, degree at most k, then the expected value of psi of h of x, where x are random bits, minus the expected value of psi of h of z, where z is Gaussians, is at most, some O times this thing with the fourth derivatives, which I'm going to kind of skip, times something that's exponential in k, times the maximum influence of h. Okay, so the maximum influence we're kind of in good shape with, since one of our hypotheses is that h or f has small influences, or these small attenuated influences. But it's this degree thing that's the problem. Okay. So what are we going to do? So the high-level idea is I'm going to get to a low-degree function in 2 steps. One thing I could do is just take my f and truncate it to some low degree and hope that somehow it doesn't change the function too much. By which maybe I mean that I might hope that f and f truncated to some low degree, these 2 functions were close in this sense. Unfortunately, that might not be true. I don't know. F, as far as we know, could have lots of Fourier mass up high. But the idea was that in that case, it probably is not going to have good noise stability anyway. So what we're going to do is first smooth F by applying the T operator, and then we'll truncate it. So actually, let me just say it more in symbols than in words, or than in, yeah. OK, so step one is given the F of the theorem, let G be T1 minus delta of F for some small delta. OK, in fact, maybe I'll just set delta to be like 1 over log 1 over epsilon. OK, something that's going to 0. And this function, it doesn't have low degree, but somehow since you've smoothed it with this T operator, it sort of almost has low degree. You know, that's high degree stuff gets attenuated a lot. So I want to claim that sort of we're almost done. And we'll say that G, we'll see now that G is sort of just as good a function as as F to work with. OK, so let's look at the properties of G given the properties of F that we know. We have the expectation of F is 0. That's by assumption of the theorem. So therefore, the expectation of G is also 0. OK, this T operator does not change the empty Fourier coefficient of F. We know that F maps into the range -1, 1. I claim, therefore, G also maps into the range -1, 1. Okay, and the reason for that is, remember, T row of F at a point X is like the average of F's values over some neighborhood of X. So if F is always between -1 and 1, then so is its average over a bunch of points. So therefore, G also maps into the interval -1, 1. And we also knew that by assumption that F's influences, even with this 1 minus epsilon stability parameter, were small. So I claim that means that G's normal influences are also small. So why is that? Well, let's look at the influence of I on G. By definition, that's the sum of the squares, the Fourier coefficients of G that involve I. And this is the definition of G. So this is just sum over S that contain I of 1 minus delta to the 2 cardinality of S, F hat S squared. OK, and delta is, this is actually a lot bigger than epsilon. OK, so this is less than or equal to sum over S 1 minus epsilon to S minus 1, F hat S squared, which is exactly equal to this. OK, so F having small stable influences implies that G has small influences. OK, so that would be good if we were going to apply this theorem with G instead of H, because this term would be small. G doesn't actually have low degree, but sort of we're almost there because it's a smoothed function. OK, that's fine, but suppose we manage to pull that off, and we got all of the rest of the proof to work with G instead of F. And what we would have done is get an upper bound on the noise stability of G. But we want an upper bound on the noise stability of F. Okay, so we may be able to get that the noise stability of rho of G, except for the problem essentially that it doesn't have low degree, we follow the rest of the proof and we get this upper bound. Okay, but we care about the noise stability at rho of F. All right, but I claim that they're close. Okay, so let's compare them, the noise stability at F and the noise stability at rho of G. Well, this is going to be the sum over S rho to the S, f hat S squared, minus the sum over S of rho 1 minus delta squared, S f hat S squared. Okay, which is, let's say at most, sum over S rho to the S, 1 minus delta, so the 2 cardinality of S, f hat S squared. Okay, and I claim that this is actually very small. I guess in the interest of time, I won't do the rest of the arithmetic, but I'll explain it in words. You see, you can look at whether S is greater than or less than, let's say, 1 over root delta. If S is smaller than 1 over root delta, it's like 1 minus delta to that power. It's still going to be pretty close to 1. So its difference from 1 would be maybe at most root delta. Okay, and so this factor would be at most root delta. What I'm going to show is this factor is actually small for all cardinalities of S. On the other hand, if S is quite big, then maybe 1 minus delta to the cardinality of 2S is not close to 1, but rho, which is just some number like a half or a third or 1 over root 2 to the S will be very small. Okay, so without finishing the arithmetic, this is sort of always, let's say, O of root delta. And so this whole thing is at most O of root delta. Okay, and delta goes to 0 with epsilon, so stability of F and G are still close. So we'll get an extra little O of 1 here. All right, I got 2 minutes left. We can do it. Okay, so as I said, everything would be great and we'd be done if we could imply the invariance to G, but we can't. It still doesn't have low degree. But it sort of morally has low degree, and the last step will be one more little tweak. Step 2. I guess this was step 1. Define H to be the low degree truncation of G. Let's say I truncated at degree delta squared. Okay, so G had mean 0. H still has mean 0 because I just dropped some high degree parts. That doesn't change the constant term. H still has small influences because, again, I just dropped some part of the Fourier spectrum, so that can only make the influences go down. So that's good. The max influence is small. And, of course, the degree of H is low. Okay, so what I'm saying is the error term, okay, I would like to apply this whole argument with H instead of G. In invariance with H, is going to be some constant times 1 over delta squared times 9 to the 1 over delta squared times epsilon. Okay, but remember, delta is like 1 over log epsilon, so even 9 to the 1 over delta squared is not a big deal compared to epsilon. So this is at most O twiddle epsilon. So everything looks great except for one catch, which is that H does not necessarily map into the interval -1, 1 anymore. Okay, so we don't have the expectation of psi of H equals 0 like we had when we had F or G there. But, and this is the last step, I claim that G is close to H in L2 squared. Truncating the high degree part of G hardly matters to G because it's already smooth. And so since G maps into -1, 1, H almost maps into -1, 1. So we can just note that G minus H2 squared. I just dropped some terms. So this would be sum over S at least 1 over delta squared of g hat s squared, which is like sum over s at least 1 over delta squared, 1 minus delta 2 cardinality of s, f hat s squared. Okay, and this thing is very small. This is like at most exp minus 1 over delta for all s. Okay, so since g mapped into minus 1, 1, we have expectation of psi of g of x equals 0, and I leave it to you to check that this implies that the expected value of psi of h of x is at most exp of minus 1 over delta. Okay, so which is little o of 1 with respect to epsilon. So finally, h has all the right properties. We can apply invariance to it. We can deduce that, the expected value of psi of h bar of z is at most little o of 1. And apply Borel to it. Get that its noise stability is small. Deduce that h's Boolean noise stability is small. H is close to g, so g's Boolean noise stability is small. And g's noise stability is close to f, so it's small, et cetera, et cetera. We're out of time, but if you watch the video again, you can fill in the details. Okay, well, I told you it was a lot of messing around. We've seen enough. Any questions? Okay, so I'll see you on Wednesday.